Hello and welcome to section 4.6. We're dealing with variation of parameters. So last section we talked about solving a second order differential equation where it was a non-homogeneous, therefore it was equal to a function. But we had certain cases where the cases do not work for certain functions on the right hand side. So now we're going to look at a method where it will work for anything on the right hand side. And so here we have a first order differential equation where it's set equal to a function, so it's non-homogeneous. And what we want to do is, in order to figure out how to use variation of parameters, we need to look at this differential equation and determine what would the actual solution be if we were to actually solve this. Now, if you look at this, you can tell that, hey, this is first order linear, so we can solve by using an integrating factor. So our integrating factor would use p of x, and so we would have e to the integral of p of x dx as our integrating factor. And then what we would do is we would multiply both sides, and so on the left hand side we would have y times e to the integrating factor of p of x dx in the power, and we have to multiply the integrating factor to both sides, so f of x times e to the integral p of x dx. And on the left hand side, the reason we can write it this way instead of multiplying it by our integrating factor to the left is because this was just a product rule, and so we can just write the derivative of that is equal to that on the left-hand side. And now in order to actually solve this, we would integrate both sides. And then on the left-hand side, we would just get y e to the integral of p of x dx. And on the right-hand side, we really can't integrate that because we don't know what our functions are. So it would just be the integral of f of x e to the integral p of x dx, and then say we were able to integrate that, then we'd also have our plus c. So we really want to solve for y. We want to find out what is the solution to this first order. Again, it's a first order differential equation. We're going to have one y sub 1, and so y is going to equal, then it's going to be c sub 1 times our integrating factor plus, and let me go ahead and put a negative there because I would be dividing it. So c sub 1 times e to the negative integral p of x d of x plus e to the negative integral p of x d of x times the integral of f of x integrating factor e to the integral p of x d of x. And so that's what our solution would be. But hopefully from here you know that a solution to a non-homogeneous equation is going to be y is equal to y sub c, which is the complementary solution, plus y sub p, which is our particular solution. Because it's non-homogeneous, this would be the solution to the non-homogeneous part. Well, if I look at this, my y sub c, it's just going to be c sub 1 e to the negative p of x d of x. So looking at this, our y sub 1 would be the e to the negative integral p of x d of x. That means our y of p would have just been e to the negative integral p of x d of x times the integral of f of x e to the integral p of x d of x. And if I look at this further, I can see that my y of p is really just y sub 1 times this part right here, which I can actually rewrite this as the integral of f of x over e, or I'll just say over y sub 1. And so therefore our particular solution is just our solution to the non-homogeneous part times some other function that we would get here if we took the integral. So therefore we can write our particular solution as y sub 1 times some function right here, and we're just going to call that function u sub 1. And that leads us to how we would solve a second order differential equation that's non-homogeneous. So say we get y double prime plus p of x y prime plus q of x y equals f of x, where p and q are just some functions of x. And so here we have a second order differential equation. Well, our solution to this for the particular part would just be y sub p is equal to u sub 1 of x times y sub 1 of x plus u sub 2 of x times y sub 2 of x. And we can derive that from right here, where y sub 1, u sub 1 are just two functions of x. I could write this y sub 1 of x times u sub 1 of x. And so this is for first order, this is for second order differential equations. Now, to see that this is actual solution and actually how to find our particular solution, what we're going to have to do is, integrate this. So I'm going to show you how to do this. If you want, you can kind of just skip through this and see how the process is done. But I want to show you how we actually get to being able to solve these. So here I'm just going to give you just a whole lot of background information of how you actually get to the method. Again, you can skip straight to the method and just use the method, but this is the background information. So say y sub p is our actual solution. So if y sub p is our solution to our second order differential equation, what I would really need is I would want to find out that this is actually a solution. So what I'm going to do is I'm going to substitute in y sub p, y prime of p, and y double prime of p. Now, again, this is not going to be fun. Oh, it's going to be fun for me. I enjoy this, but you might not think this is fun because there's going to be a lot of product rules here, and it's very easy to mess up. So hopefully I don't mess up as I do this, recording this, but we'll see. But I probably won't make a mistake, just because I shouldn't. So we have, so we want to take the derivative of this, so we have product rules. So I'll take the derivative of the first. Now, I'm just going to write this as, just to save on some notation, y sub 1 of x, y sub 1 of x. I'm going to write y sub 1, y sub 1. They're just both functions of x, plus u sub 2 times y sub 2, both of those functions of x as well. And so the derivative would be the derivative of the first times the second, plus the derivative of the second times the first. So it's just going to be u sub 1 prime times y sub 1 plus y sub 1 prime times u sub 1. And then let's take the derivative of the second. So plus u prime, u sub 2 prime times y sub 2 plus y prime of y sub 2 prime times u sub 2. And therefore we took the derivative of we took the first derivative. Now we want to take the second derivative. So we're going to do y double prime of p. And so look at this, and I'll take the derivative. So the derivative of u sub 1 prime is u sub 1 double prime times y sub 1, plus the derivative of y sub 1 is y sub 1 prime times u sub 1 prime. Plus, now let's take the derivative of this one. Y sub 1 double prime times u sub 1 plus u sub 1 prime times y sub 1 prime. Go to the next one, plus u sub 2 double prime times y sub 2 plus y sub 2 prime times u sub 2 prime. And then let's do the last, so plus y sub 2 double prime times u sub 2 plus u sub 2 prime times y sub 2 prime. All right, I just want to check to make sure I didn't make a mistake. Doesn't look like I did, so let's now continue. So let's plug these into our differential equation, y double prime plus p of x, y prime plus q of x, y equals f of x. So I'm going to substitute this in first. So this is going to be fun. So I have u sub 1 double prime, y sub 1, plus y sub 1 prime, u sub 1 prime, plus y sub 1 double prime, u sub 1, plus u sub 1 prime, y sub 1 prime, plus u sub 2 double prime, y sub 2, plus y sub 2 prime, u sub prime 2, plus y sub 2 double prime, u sub 2, plus u sub prime 2, y sub prime 2, plus p of x times all of this. So I'm just going to go ahead and substitute the p of x. I'm going to go ahead and distribute the p of x into that. So u sub 1 prime y sub 1 plus p of x y sub 1 prime plus times u sub 1 plus p of x u sub 2 prime plus y sub 2 plus p of x y sub prime to u sub 2, and then plus q of x times our original, I'm just going to use q's and p's, I'm going to do that in a second. So q of x times our y sub p, which is going to be u sub 1 y sub 1, plus q of x u sub 2 y sub 2. Alright, and all of this equals f of x. So now I'm going to try and bring a lot of this together, and so therefore I'm going to say u sub 1 is, and this is all equal to that, u sub 1 is equal to, so u sub 1 times, and now what I'm going to do is I'm going to try to find all my y sub 1s and write them down. So it looks like I have y sub 1 double prime plus, find p of x, not that one, p of x times u sub 1 prime times y sub 1 prime plus, and then if I go over here, I'm going to have q of x times u sub 1 times y sub 1. And so now I have u sub 1 written, all my u sub 1s written as this according to these methods. And so I'm going to underline those. This is not one that I meant to underline, so we'll deal with that in a second. And I got it from here. And now I'm going to do that same thing with my u sub 2s. And so here you see I have a u sub 2 with a y double prime. So I'm just going to have y double prime with 2, sub 2. Then I'm going to do with my p of x, which I have a u sub 2 right here with a y prime. So it's going to be plus p of x y prime of 2, y sub 2 prime, and then plus q of x, and I'm going to pull that from right here, which is going to be times u sub 2 y sub 2, and I have my u sub 2 out there, and so it's written that way. And then I'm going to save some space, that's plus, so this is still all part of 1. And I'm going to now pull out some other parts. So I'm going to have y sub 1 u sub 1 double prime, pull that from right here, and then I'm going to also pull out u sub 1 prime, so plus u sub 1 prime y sub 1 prime. All right, and then pull that from right there. Let's put, give those little marks. And then plus, I'm going to do the same thing with my y double primes and u double prime. So I'm going to have u sub 2 double prime, u sub 2 double prime, y sub 2. And then I'm also going to have pull out the next term, which is going to be plus y sub 1 prime, sorry, not y sub 2 prime, and u sub 2 prime. And then again, I pull those right there. All right. And then I'm going to have all my p's together, so plus p of x, and all the other terms that had my p of x's, I'm going to write, so u sub 1 prime y sub 1, that's going to be right there. And then this one, u plus u sub 2 prime plus y sub 2, not to plus, but times y sub 2. And then plus, let's see, the only thing that I have left, I have an additional u sub 1 prime, y sub 1 prime, plus u sub 2 prime, y sub 2 prime. And all of this equals f of x. Now, the reason I wrote it this way is so that you could see that, hey, this was a solution to our our homogeneous part, because y sub 1s and y sub 2s are part of the solutions to the homogeneous part. So all of this row right here, this really equals 0, and this, all that equals 0. Because these two equal 0, it's like this goes away. Now, if you can tell here, y sub 1, u sub 1 double prime plus u sub 1 prime, y sub 1 prime, that is just, if I took the derivative using a product rule of u sub 1 prime, y sub 1, and then the same thing happens here. These are just a product rule. If I had u sub 2 prime, y sub 2, and then plus my p of x times the same thing, which is going to be u sub 1 prime, y sub 1, plus u sub 2 prime, y sub 2, plus u sub 1 prime, y sub 1 prime, plus u sub 2 prime, y sub 2 prime, and that equals f of x. Well, what we really want here is we already know what our homogeneous solutions are. That's going to be our y sub 1s and our y sub 2s. What we really want to find out is u sub 1, u sub 2. So I have two functions. Not two functions, but I have two variables. And so because I have two variables, I want to see if I can find two functions that will help me solve for my variables. So what I'm going to do, and I'm going to go to the next page to do that, is I'm going to take my parts right here, and I need to figure out a way to make two sets of equations. Well, one thing we know out of here is if I make u sub 1 prime, y sub 1, plus u sub 2 prime, y sub 2. Since I have that in both of these parts, if that was equal to 0, then what I could do is I could set this part equal to f of x. And that's what we're going to do to make a system of equations. So we're going to have u sub 1 prime times y sub 1 plus u sub 2 prime, y sub 2. And we're going to set that equal to 0. Because if that equals 0, then this would equal our function. And so we're going to do u sub 1 prime times y sub 1 prime plus u sub 2 prime, y sub 2 prime, and we're going to set that equal to f of x. And now we have a system. And now, how we're going to solve this system is we're going to use the Wronskian. And in pre-calculus, you were probably taught how to solve a system of equations using Cramer's rule, and that's what we're going to do here. We're going to use Cramer's rule. And Cramer's rule, all it is that we're going to be able to solve for our variables by using the determinants. And so, therefore, I can actually solve using the determinants. Now, I'm going to show you what that is, but first I'm going to write the Wronskian. So the Wronskian is just going to be our first terms, y sub 1, y sub 2, and then we just take the derivative of that, and then we're just going to set that equal to, and then we'll set that equal to 0. That's the Wronskian. Now, why you could use this in pre-calculus is because you're just taking the variables down, y sub 1 and then y sub 1 prime. And so you're just taking those. Now, what we want to do is we also want to we're going to call this Wronskian sub 1, which is just basically what we would use to find, all right, so the missing variable. So if we want to solve for, u sub 1 prime, because that's going to be our first variable, this is u sub 2 prime is our second variable, what we do is we eliminate the first part, our first column, that's why it's sub 1, with our we substitute in our solutions, and we're going to multiply that by, and we're going to keep the second column the same. So that's w sub 1. Now, w sub 2 is where we're now going to keep the first column, and we're going to multiply, or not multiply, but then our second column is just going to be the solutions. And that's what basically Cramer's rule is, where I'm able to find my first term, my first variable, u sub 1 prime, And that's just going to be equal to, and Cramer's rule is, and I don't want to tell you anything, is where we're going to take our W sub 1, which is going to be these are all the determinants, divided by the Wronskian. And that's what U sub 1 prime is. Now, when you do all the math and you find out, okay, what we really have, we really are just going to have, this is always going to just come out to be, for the Wronskian sub 1, it's just going to be negative f of x times y sub 2 over w. And again, Cramer's rule for the second one, or second variable, should be just prime, u sub 2 prime, is equal to the Wronskian sub 2 divided by the Wronskian, which this is just always going to come out to be f of x, y sub 1, divided by our Wronskian. And now, once we find out what u sub 1 prime is and u sub 2 prime is, then all we have to do is take the integral, and once we take the integral of both of those, we're able to find out what u sub 1 is and what u sub 2 is. Once we take once we integrate that, then we'll be able to find our solutions, and then we can write it in the form y sub p is equal to u sub 1 times y sub 1 plus u sub 2 y sub 2. And then that will be our particular solution. And so the summary of the method is this, all right? And again, this is where you can just skip back down to this last section, is we're first going to find, so the first thing that we need to do is we need to find our complementary solution, meaning that we need to find the solutions when we set it equal to 0. So we set up the auxiliary function, and then we find our y sub 1 and our y sub 2. After we do that, we need to make sure that our equation is in standard form, meaning that y double prime is by itself, all right? So the coefficient, the leading coefficient is 1. After we do that, we take the Wronskians, we set up to find our u sub 1 prime and our u sub 2 prime. Once we do that, we can integrate that, and then we're going to have our y sub 1, we'll find our particular solution, and then we can just plug it into the general solution.